This presentation is entitled Connection-Taxonomy-Based Transitive Closure Maintenance. A real mouthful. It's an advanced feature. First of all, transitive closure is a clever way of doing graph navigation in a relational database. And typically when you write a query with transitive closure, you're specifying a connection type. So for example, let's say we have a connection type called causes and another one called treats. Okay, I can write a query looking for all causes kinds of relationships. I can write one that says all treats kinds of relationships. But what if I want to ask a higher level kind of connection query? So you can imagine for a minute that causes and treats are specializations of a more general kind of relationship, let's say associated with. So what this enables you to do, this particular technology, is write what are called polymorphic queries in terms of connection types. So I can write a query that says find all associated with kinds of relationships, which underneath the hood would then look at things like causes and treats.
Connection-Taxonomy-Based Transitive Closure Maintenance. Information technology has a number of challenges associated with it. For this presentation, we're going to look at two, something called fragility. It's the case where you have an enterprise system, typically an n-tiered architecture, where one of the layers changes and causes a ripple effect, breaking other layers. The other challenge is one called rigidity. It's the inability to easily modify data schemas on the fly. To address the challenges identified on the previous slide, we're going to use a technology called TCSQL. In particular, we're going to look at its capability of being able to take a taxonomy of different kinds of connections and be able to apply transitive closure to multiple kinds of connections identified in that taxonomy. We're going to start by doing a little graph theory here. In front of us are two graphs, a family tree and a graph of bus routes. Some of the components of a graph consist of the following: the notion of something called nodes. In this family tree graph, the nodes happen to be the names of people here. A second component of graphs are these things called connections here, or edges. And they happen to be the arrows we see between nodes here. Sometimes in graphs, you have a semantic relationship associated with these arrows. In this family tree graph, we have a father of relationship, and we have a mother of relationship. Sometimes with graphs, you have scalar values associated with the connections. In this bus routes example, the scalar value represents a cost of going from one city to another. The notion of transitive closure is a concept that is foreign to most people. So let's look at a definition of transitive closure. Given a graph G, the transitive closure of a graph is the set of all potential paths between all nodes in the graph here. So in fact, the transitive closure of a graph can be represented using a relational table here. So the way to think of the population of this table, you can think of it as follows. Take any two nodes in the graph, let's say starting with n1 and looking at n6. Does there exist a path, directed path from n1 to n6? The answer is yes. Therefore, we see a transitive closure record here. Does there exist a directed path from n2 to n6? Notice I say the word directed, you got to follow the directions of the arrows. The answer is no. So n2, n6 does not show up here. So what can you do with the transitive closure of a graph? You can use it to navigate a graph. So if we want to know all of the descendants of n1, what we can do is write a select statement as follows. Select child from transitive closure where parent equal n1. Now let's play computer a second here and let's execute this query here. Let's find all the rows here where the parent has a value of n1. We see that in green here. And let's find all of the children from all those records. And what we find is we get n2, n3, n4, and 5, n6. So in fact, that represents all of the descendants of n1 here. Now one of the unique things about transitive closure with respect to TCSQL features the ability to maintain transitive closure in a graph as a graph changes. So normally, if you're adding or deleting nodes or connections in the graph, what happens is you typically have to rederive the transitive closure from scratch. one of the features of TCSQL is its ability to maintain transitive closure whenever nodes or connections are added or deleted from a graph. Let's look at TCSQL's support of multiple transitive closures. Imagine the following. Imagine you have these different connection types here. And we have the following here. We have node A going to node B via a leads to connection, going from B to C, also a leads to connection, going from C to D via a results in connection, and D to E in a pertains to connection. And imagine the following, that there is a taxonomy associated with these different connection types here. So leads to and results in are specializations of this more general kind of connection called effects. Effects and pertains are specializations of this more general kind of connection called association here. So let's imagine, how would we navigate from A to E using transitive closure here? Well, normally here, you would have to do the following. You would have to have 3 copies of the transitive closure tables here. You'd have to have one to go from A to C, since both of these are the same connection. You'd have to have another one going from C to D, and one going from D to E, so that shows up here. But what if we do the following here? It turns out leads to and results in are special cases of this effects here. So if we maintain a transitive closure here of effects, that means we only need 2 copies of the transitive closure. So our select statement looks like the following, only 2 copies here. Now if we generalize it even further here, we recognize that all of these are special cases of this most general kind of connection called association. So in this case, we only need 1 copy of the transitive closure table. So what can we learn from this? Well, first of all, solution 1 ends up requiring the least amount of space in terms of maintaining transitive closure. And solution 3 is the most general type. You don't have to hard code, you don't have to have hard-coded knowledge as to the different kinds of transitive closure you're going to need here. So TCSQL has the ability to flip a switch in defining the connection definitions here that allows support of multiple transitive closures. So why is this valuable? Well, first of all, it demonstrates the ability to do polymorphic connection queries here. We talked about polymorphic queries in the past with respect to class nodes. Now we're talking about the ability to provide that polymorphism with respect to class connections here. And secondly, as I talked about in the last slide, it allows the designer to make a time versus space trade-off in terms of transitive closure maintenance.